Today we are going to discuss infinite geometric series. So infinite arithmetic series is always divergent. Arithmetic series is when we are adding or subtracting the same factor from subsequent terms. That series is always divergent. But infinite geometric series is sometimes convergent, sometimes divergent. So let's see first of all, what is a geometric series? Geometric series is when we multiply each subsequent term with the same factor. We could be multiplying with a 3 every time. So my term can be 1 and then multiply with 3, multiply with 3, multiply with 3, and so on. Or we could be multiplying with 1/2, which means your terms are going to be getting smaller and smaller if you're multiplying with 1/2. So if you're multiplying with 1/2, my terms will be 1, 1/2, 1/4, 1/8, 1/16, and so on. So here's an example, another example. My first term is 3. I could be multiplying with the 2, and again multiply with the 2, again multiply with 2. So keep on multiplying with a 2 as we go on. General form of geometric series is summation n equals 0 to infinity a r to the power n, where a is your first term and r is the common ratio. So r is common ratio. That's the number you're multiplying with as you go, and a is the first term. A is the first term. R is common ratio, A is first term. Sometimes it's represented by A1 as well, which is both are okay. Convergence of a geometric series. A geometric series with the ratio R greater than 1, if the absolute value of the common ratio is greater than 1, that series always diverges. If the absolute value of R lies between 0 and 1, then the series converges to the sum here. The partial sum of geometric series is given by Sn is equal to a 1 minus r to the power n over 1 minus r. We can use this formula to find the sum of first 5 terms, first 20 terms, first 100 terms. We can use this formula to find sum of Sn terms. And we just said that the sum converges to a over 1 minus r if we are considering the infinite terms. As long as your absolute value of r is between 0 and 1, absolute value of r is less than 1, then the series will converge. If absolute value of r is greater than 1, then the series will diverge. Okay, so S infinity is going to be a 1 minus r to the power infinity over 1 minus r. Now we just said r is very, very small because r, absolute value of r is less than 1. That means r is a very small fraction lying between 0 and 1. So this term will go to 0. When we raise a very small fraction to infinite power, it's going to eventually go to 0. And that's how the sum is a over 1 minus r for infinite terms. Let's see some examples. Convergent and divergent geometric series. Determine the convergence or divergence of the series. If the series converges, find the sum. So here, my common ratio, we have n is equal to 0 to infinity, 3 times 1 over 2 to the power n. What is my first term here? When n is 0, my first term is going to be, I'm going to plug n as 0, my first term a is going to be 3. Or we can call it a1 if you want to. That's just to know that's my first term. What is the absolute value of r in this case? What number am I multiplying with each time I go? I'm multiplying with 1/2. For the 0th term, for the first term, I'm going to be multiplying with 1 over 2 to the 0 power, which is just 1. And the second term, I will be multiplying with 1 over 2. Third term, 1 over 2 square. Fourth term, 1 over 2 to the third power. So I'm multiplying with 1/2 as I'm going. And absolute value of 1/2 is less than 1. That means the series converges. Because the common ratio is less than 1, absolute value of common ratio is less than 1, the series converges. Now we want to find out what does it converge to. So sum of infinite terms is going to be a over 1 minus r. And we just found the a is 3 and the r is the common ratio, which is 1/2. 3 over 1 minus half is 1/2. So it turns out to be equal to 6. So that means the series converges to 6. This series converges to 6. So if you go ahead and add many terms of this series, then those terms, sum is going to be convergent to 6. The sum is going to be closer and closer to 6 as you're considering more and more terms. The next example here, when n is 0, my first term is going to be 3 half to the 0 power, which is 1. When n is 1, my second term is going to be a times 3 half to the first power, which is 1 times 3 halves. So here we can see each time we go, we can write first few terms if we want, but I can see my first term is a, which is 1, second term is 3 halves, the next one is going to be, I'm going to be multiplying with the 3 halves again, and then again and again. So each time I'm multiplying with the 3 halves. So common ratio r is equal to 3 halves. In this case, r is greater than 1, 3 halves is greater than 1. If absolute value of r is greater than 1, then the series diverges. That means we cannot find the sum of this series. It doesn't converge. It doesn't get to a particular number. As you're adding more and more terms, the sum is getting bigger and bigger. Another example, square root of 2 raised to the kth power. Can I think of it as 1 over square root of 2 to the k power? That means each time I'm multiplying with the square root of 2. And what is my common ratio r here? That's 1 over root 2. And that is smaller than 1. That means the series converges. Series converges. So if it converges, we want to find the sum of the infinite terms, which is going to be a over 1 minus r. What's going to be a over here? If I plug k as 0, anything to the 0 power is 1, and the common ratio is 1 over square root of 2. Let's go ahead and simplify it. That would be 1 over square root of 2, root 2 minus 1, which turns out to be, we have 1 divided by root 2 minus 1 over 2, turns out to be 1 times 2 over root 2 minus 1, which is 2 over root 2 minus, that was a root 2 as well. Yep, root 2 minus 1 over root 2, and that would be root 2 here as well. Okay, so that is the sum of many terms. When you consider 100, 200, 500 terms of the series, the sum is going to be getting closer and closer to this particular number. The more terms you consider, more closer your sum will be to this number. Okay, the next one is 3n plus 1 over negative 2 to the power n. Doesn't look in a very good shape to me, so I'm going to try to rearrange and rewrite it. This is going to be n is equal to 0 to infinity. I can write it as 3 to the power n times 3 over negative 2 to the power n. Now, n is equal to 0 to infinity. 3, can we pull out, we can just leave the negative in there. So it would be 3 over negative 2 to the power n. We can just rearrange it. Now my common ratio r here is negative 3 over 2. And absolute value of r is greater than 1 actually. Absolute value of r, not just the r. We're looking for absolute value of r is greater than 1. That means this series diverges. If absolute value of r is greater than 1, then the series diverges and we are not able to find the sum of such series. Another example, summation n equals 1 to infinity. Again, this is not in a very nice shape and form yet, so I'm going to try to rearrange and see if it is like a geometric series. I'm going to write it as 2 to the power 2n minus 2 to the power 2n times 2 to the power negative 1, right? Yeah, over 3 to the power n. Summation n is equal to 1 to infinity. I can write it as 6 over 2 because 2 to the negative first power can come down, and I can write 2 squared over 3 to the power n, right? So it turns out to be summation n is equal to 1 to infinity. 6 over 2 is 3, and 2 squared is 4 over 3 to the nth power. Now here, 4 over 3, again, the common ratio here, common ratio r is 4 over 3, and absolute value of r is greater than 1, thus the series diverges. Be very careful. We are talking about the series, we are not talking about the sequence. Last section we talked about the sequence. In that section we were talking about the 100th term, 200th term, 2000th term. Are they converging to a particular number? Now we're talking about sum of all the terms of the series. Okay, rational number is a number that can be expressed as a ratio of two integers. All rational numbers can be either expressed as terminating decimals or repeating decimals. Irrational numbers are non-terminating, non-repeating decimals. So express the given decimal as a ratio of integers. So we have 10.1 3, 5 with a bar on the top, that means the 3, 5 is repeating. And we need to find out if we can write it as a ratio of integers. So let's see. Can I say this is 10.1, 35, 35, 35, 35, 35, 35, and so on. It goes on forever. So I can say this is 10.1 plus 35 times 0.001 plus 35 times 0.00001 plus 35 times 0.0000001, and so on. So this actually becomes a geometric series now. This becomes a geometric series with a given first term, which is 10.1, and the common ratio is 0.001. So my A is 10.1 and the common ratio is 0.001. So we can express it slightly differently as well, if that's easier. 10.1 plus 35 over 10 to the third power plus 35 over 10 to the fifth power plus 35 over 10 to the seventh power, and so on. And now we can easily see what number are we multiplying with. We are multiplying with 1 over 100 each time we go. So my A is 10.1 here. The common ratio is not 0.001 here. That wasn't the common ratio. The common ratio is going to be 1 over 10 squared. The R is 1 over 10 squared, which is 1 over 100, which is 0.01. 0.01, right? So this is 10.1. Okay, once we found out our R and we have our A, we can write the sum of this series, because that's what this is. This is the sum. That is going to be, we can express it as A over, actually, let's look at it again. This is not, the series starts here. Series start here. 10.1 is just added in the front. 10.1 is not a part of the series because we're not really doing anything to 10.1. So go back, A is not 10.1. 10.1 is not even a part of the series. 10.1 is separate, and this is my geometric series. My geometric series starts here. And what's going to be my sum of the geometric series? Sum of the geometric series would be 10.1 plus the A first term, which is 35 over 10 to the third power, over 1 minus R, which is 1 over 10 squared. So now we would go ahead and simplify it using a calculator, and that's a way to express this. We wouldn't call it sum because we are just rearranging it or expressing it in a different way. Our eventually goal was to call this number as a ratio of integers, or express it as ratio of integers. That would be 10.1 plus 35 over 1,000 times, that would be 100 over 99 in the denominator. Now see what we can cancel here. That would be 10.1 plus 35 over 990. And now we can express it as, we can add or subtract and simplify it more using calculator. So we have expressed this non-terminating repeating decimal as a ratio of integers. Alright, so next we have properties of infinite series. If summation of an and summation bn be convergent series and a, b, and c be real numbers. So if sum of the an is a, sum of bn is b, then the following series converge to the indicated sum. So if we multiply a series with a constant, then we can just multiply the sum of the series with the constant. If we add or subtract the series and the series converge, we can add or subtract their sums. Nth term divergence test, very, very important test. Nth term divergence test of series. This is a test to tell if the series is convergent or the series is divergent. So this test does not tell us anything about convergence. That's just the name. The name says this series only tests for divergence. That's why it's called nth term divergence test. But it's a test for series, not for the sequences. This test tells us if the series diverges. If it doesn't diverge, we cannot say it's divergent or convergent. It doesn't tell us anything about convergence, but it definitely tells us about divergence. Here's what nth term divergence test is. Nth term divergence test says if limit n goes to infinity, a of n is not equal to 0 or it does not exist, then the series diverges. So the nth term, if we can express the sequence with the an sequence, and the nth term, limit n goes to infinity, the nth term is not equal to 0 or it does not exist, then the series diverges. If limit an is equal to 0 as n goes to infinity, then we cannot say anything. We have to use another method to determine the behavior of series. The converse is not true. That means if limit n goes to infinity, an is equal to 0, the series could converge or it could diverge. So memorize the only thing nth term divergence test tells us: if limit n goes to infinity, an is not equal to 0 or it does not exist, then the series diverges. That's all it says. A few helpful tips. Infinite arithmetic series always diverges. Infinite arithmetic series is never convergent, it is always divergent. Infinite geometric series, just like we saw now, it can be convergent or it can be divergent depending on r. Absolute value of r is less than 1, then we have convergence. Absolute value of r is greater than 1, then we have divergence. Or even if it's equal to 1, we have divergence. Limit of a rational function: if you have a top heavy function, the limit goes to infinity. Bottom heavy function, the limit goes to 0. If we have same degree numerator and denominator, the limit would be leading coefficient of top over leading coefficient of bottom when n goes to infinity. Let's see some examples of nth term divergence tests. So we're going to use nth term divergence test. Again, nth term divergence test says if limit n goes to infinity, an is not equal to 0 or it does not exist, then the series diverges. Okay. Let's see first example. So we're going to go ahead and find limit n goes to infinity, 2 to the power n. So this is equal to infinity. It is not equal to 0 and it does not exist, so this series diverges. Limit n goes to infinity, n factorial over 2n factorial plus 1. So here we kind of have the same power in the numerator and denominator. This limit is going to go to 1/2. So this, again, this is not equal to 0 or it does not exist, then the series diverges. It is not equal to 0 and it's not equal to 0. So if it's not equal to 0, that means the series diverges. So we can say the series diverges. We're going to learn many tests to find out about convergence and divergence of series in this chapter. It is just the beginning. So summation n equals 1 to infinity 1 over n. Limit n goes to infinity, 1 over n. Well, this turns out to be 0. So if we get a 0, the nth term divergence test does not apply. Nth term divergence test does not apply. That test does not tell us anything about convergence or divergence of this series, so we cannot say anything. This is inconclusive based on the nth term divergence test. We cannot say anything in this case. Let's check out the next one. Summation k is equal to 1 to infinity 1 over k to the power negative 0.01. So let's go ahead and find the limit. Limit k goes to infinity. I would just take it to the numerator because the exponent is negative in the denominator. So when k goes to infinity, this limit also goes to infinity. So we can say it does not exist, which is infinity. We don't know where that is. That means the series diverges. Maybe I should add here that if the limit is not equal to 0 or it's infinity, then the series diverges. Does not exist means infinity is also does not exist. Okay, summation n is equal to 1 to infinity n over n squared plus 1. We're going to go limit n goes to infinity n over n squared plus 1. That would be, when this is a bottom heavy polynomial. To show work, we would divide numerator and denominator with the n Or we can also say that we can use L'Hopital's rule. This is infinity over infinity form. L'Hopital rule says that we can take the derivative of numerator over derivative of denominator. When n goes to infinity, this limit goes to 0. Again, based on nth term divergence test, so we can say nth term divergence test is inconclusive here. Divergence test is inconclusive in this case. Based on that test, we cannot say anything in for this problem. Okay, let's see. I'm going to add one more. Summation n is equal to 1 to infinity negative 1 to the power n plus 1. What would happen to this series? Would it converge? Let's go ahead and take a limit. Limit n goes to infinity, negative 1 to the power n plus 1. When n goes to infinity, where does this limit go? Well, it is going to be switching, and n is 1, n is 2, n is 3. It's going to be switching between positives and negatives. So this limit does not exist because it is switching between positives and negatives. So we can say this limit diverges. This limit diverges. That's all for this section. We talked about, in this section, we started with geometric series, and we looked at nth term divergence test. So this nth term divergence test does not tell us anything about convergence. It only tells us about divergence.